hope this sounds like an important lesson since we're working on the fundamental theorem of calculus. So you will get used to seeing the letters FTC. The fundamental theorem of calculus comes in two different parts, and we'll be working on this and looking at the proof of the fundamental theorem over the course of a number of different lessons. First, let's get used to just using the fundamental theorem, and if you're not quite sure about the proof, that will come in time as we do some more repetition. So notice here that we're learning that the derivative of an integral is somewhat of an undo process. So some things that we'll notice here is that we have the derivative with respect to x of an integral from a constant a to the upper limit of x. So what we find out in this theorem is that we get right back to the integrand with one change. So notice what has happened. Our response here is the integrand. However, the independent variable t has been replaced with x. So let's work on that process, and then we'll see again why that happens as we do additional repetition throughout the next few days. So what you need to check on here is, are we doing the derivative of an integral? Remember, an integral accumulates the area. So here we're accumulating area under a sine curve, and we're asked to do the derivative with respect to x of an integral that goes from a constant pi to the variable x. So we need to check several things here. So we need to differentiate with respect to the same independent variable as the upper limit. So we need to check that this is the same variable, and we want this lower limit to be any constant. So here pi serves as a constant. So if we did the integral, that would require an antiderivative. But if we differentiate an antiderivative, we'll get right back to the integrand. So the only thing you have to remember is that we replace that variable with the value of x. In our next example, check again here. Do these two variables match? Our upper limit w and our accumulator function, g, is accumulating the area under this logarithmic function. Our lower limit is a constant. So our fundamental theorem tells us that if we find g prime, if we do the derivative of this accumulator function, we'll undo the integral. And what we have to remember is that this variable will be replaced. So we'll get right back to the integrand, but our independent variable will now take the place of the p variable. And that's really all there is to it. So if we differentiate an integral requires anti-differentiation. So the derivative of an integral, we return to the integrand, but we have to make that substitution of variables. And here, of course, is the part of calculus that we can easily forget every time. We're differentiating with respect to z, and our upper limit has a z in it, but it is not just z, it is 2z. So notice that this time our upper limit is going to have a chain rule. So we still do the same process. We put our upper limit into the integrand. So we're going to get right back to the integrand, replacing the variable with our upper limit, and then we have to remember to do a chain rule on that 2z. So that is the easiest thing to forget in calculus, chain rules everywhere. So then we would cancel this 2 with this 2, and we'll get back to 7 over 5z. All right, so here we have the same situation. Notice we check that our accumulator function, function h, is equal to the integral of the sine wave as we go from 100 to the square root of q. So notice these two variables have to match. And again, our lower limit has to be a constant. And then we're going to differentiate. So to find h prime of q, to find the derivative of our accumulator function, this is the accumulation function. If that function is equal to an integral, then its derivative gets us right back to the integrand, except we need to replace our variable with our upper limit. So we'll have sine of the square root of q, and the square root of q has a chain rule, 1 over 2 square root of q. And you could move that term in front, or you could write it as a fraction. So either one of these choices, sine of square root of q over 2. Let me try to write that as a single fraction. Hopefully you're wondering why we're not working on the constant as the lower limit. Remember, we've already seen one proof of this theorem. Remember that when we do the derivative of the constant term, that will always be 0. So that's why we're ignoring that constant term. So we're going to look again at that proof in class to make sure that everyone understands why this fundamental theorem is working. All right, now we have one problem. If our variable is not the upper limit, so our properties of integrals here, remember that we would like this x to be the upper limit, not the lower limit. So we know that if we reverse the limits of integration, we know that we get the opposite value of the function. So I'm not doing anything here except I've swapped the upper and lower limits. So then we get the opposite value for our integral. And now we're ready to find the derivative. We want to find dy dx. So y is now our accumulator function because it's equal to an integral. So when we differentiate y with respect to x, we're going to get right back to our integrand, except we have to replace our variable. And notice it appears in 2 places here. Whoops, and I forgot my negative sign. Let me get that back in here. So one more time here. I forgot that I have this negative sign out in front. And then we replace our t with x. And we would replace every occurrence of that t variable with our x term. And now we move to our second part of the fundamental theorem, and we'll call this the evaluation theorem. So we're trying to integrate function f. We know that an integral requires anti-differentiation. So we're using capital letter F to represent any antiderivative. So remember, there's a family of antiderivatives when we add our constant of integration c. So we can pick any of those antiderivatives for our capital letter F. So it makes sense that we might choose the simplest and let c be equal to 0. So if we can find an antiderivative of the integrand, so let's try some examples here. So do we know what 3x squared is the derivative of? So we're reversing our power rule. So remember, we're going to add 1 to the exponent and then divide our coefficient of 3 by this exponent of 3. So indeed, you can check our term here. If I differentiate x cubed, will I get back to 3x squared? And then we take the 1. 1 is the derivative of x. So there's our capital letter F. That's our antiderivative. And now we use this notation to show that we still have to do the step where we're going to substitute 3 into our capital letter F. So this glob here, this binomial, is our antiderivative. And now we're going to take that f of 3 minus the f of negative 1. So we're simply going to take our upper limit 3 and we're going to put it into these 2 values. So when we put our value of 3 in here, we'll have, and in the future you won't show this step, you'll have our 3 to the third plus 3. And then we're going to evaluate at this lower limit of -1. So we subtract and we put -1 into our function. And of course you'll do that arithmetic immediately. So here we have a 27 plus 3 is a 30. And here we have a -1 plus another -1. So we're subtracting a -2. So our value for our integral comes out to be 32. So you will quickly get used to this idea of capital F of B minus capital F of A. Find an antiderivative, and then we have to evaluate it at our upper limit and our lower limit. So with some repetition, this will become pretty simple. So in this next example, I look at our integrand and our antiderivative. What has a derivative of 1 over x? And that would be the natural log of x. And we can put absolute values here. Absolute values won't be necessary if you're using positives only. So again, let me explain. Why did I pick natural log of x? Because it has a derivative of 1 over x. So I'm doing an antiderivative. And now this notation says take your antiderivative. This is our capital F. And now we want to evaluate it at the upper limit. So that'll be our capital F of B. And then we want to subtract our value of the antiderivative at A. So to finish this up, we're going to do the natural log of e to the 5th. I don't need absolute values since that's positive. And our natural log of e to the -2. So we have a 5 minus a -2, and we'll get 7. Remember what we're finding when we evaluate an integral. We're evaluating the area under the curve is one interpretation of that integral. All right, what are some other problems that can come up here? Well, we might be trying to find an area under a curve that is not always positive. So in this example, I've chosen a parabola that's easily factorable. So notice we know that this parabola has intercepts at 0 and at 2. And if we want the area from -1, we want the area from -1 over to 4. So some of that area is going to be above the axis and some below the axis. So if we want to find the total area as opposed to the net area, so the word total is going to always be a big signal to you to do the problem carefully. So our total area here, we would have to separate into 3 separate integrals. And then what we would do is we would take the absolute value of this middle term if we want to make this positive. So this term right here, we could actually put a minus, since we know that's the region from 0 to 2, that's the region that's below the axis. So notice in my next step here that I have absolute values. What that area is going to turn out to be negative. So I did my antiderivative of x squared by reversing the power rule, and the antiderivative of -2x is negative x squared. And then here's my f of 0, and here's my capital F of -1. And I did that 3 times for each of the 3 integrals. And then we get these 3 areas here. So we get a 4/3, and here we'll have the absolute value of -4/3. So since we want total area, we want to make it all positive. And then here we have our 20/3. So that's how you would come up with that area. So if you're allowed to use your calculator, an absolute value you can find in the catalog of your TI-89, you would think that you'd be able to just do this integral in one step on your calculator. Unfortunately, sometimes when you plug that in, you'll find out when you hit the enter key that it doesn't give you a numeric answer. It gives you back the same value that you entered. And that generally seems to happen. The TI-89 can't evaluate integrals surrounding the zeros of a polynomial. So in that case, you'll notice here that I did 3 separate integrals on the TI-89, and same problem as up above. So we made this one positive, so use the absolute value of that middle interval and then add up those 3 areas. So the absolute value, when we put absolute value into the integral on your TI-89, it will generally work. So here, let's see the difference if we did the integral. This is a screen capture from your TI-89 screen. If we were finding the area under the x cubed graph from, and I'm kind of exaggerating the curve here, from -1 to 4, you can see that some of that area would be negative and some of that area would be positive. So the area under the x cubed graph from -1 to 4 is not the same as the area if we do absolute value. So remember what absolute value does to that curve is it flips the part that used to be negative up to be positive. So the absolute value serves the purpose of taking any y coordinates and moving them above the x-axis. So notice that our integral got larger when we did the absolute value function. And here's another example of a e to the x curve moved down 1 unit. So we know what that would look like. I hope you know what that would look like. This e to the x moved down 1 unit. And we're evaluating from -1 to +4. So if we do absolute value, then we know what's really happening is that this part that was below the axis is getting reflected up here to be this red area. So putting in absolute value, and again, how do you find that? You can type the letters A, B, S into your TI-89, or you can use the catalog key, and absolute value is first since it's alphabetically beginning with A. All right. You'll be able to practice those. Some questions to check your understanding. If we evaluate a definite integral, do we get a variable expression or a constant? And here we get a constant. And we know that it comes from taking the antiderivative of b minus the antiderivative of a. And one of our interpretations is the area under the curve. So it is numeric, as opposed to an indefinite integral is a family of curves. Question 2, how would you find the net area? So net area rather than total area. So no absolute values. So here's our A value and our B value for our limit. So we're evaluating from 7.2, I didn't leave much space here to write, 9.3 of v of t, a velocity function. And I think that's all we're being asked to do here. So do not use absolute value if you want the net area. So remember what this would give you is displacement or net distance. If we did the total area under that velocity curve, when we do the absolute value, then we would be finding the total distance. And that's an important point that you'll want to remember for application problems. Question 4, what's another way to write this? Notice we're doing n going to infinity, and here we have an f of x value. This value right here would be our height of each rectangle. That would be our f of x sub i's or f of c sub k's, depending on which textbook you're using. And our delta x represents the base of each rectangle. So this is our definition of an integral, an infinite sum of Riemann rectangles. So here we're going from a to b. So if we write this using our definition of integral, our limits would be 44 to 213, And our f of x, our integrand function, would be natural log of x. And the delta x is replaced with dx. As we do an infinite number of rectangles, the delta x goes to 0. And that is what we're being asked in question 4. So you might first say, well, delta x is our formula b minus a over n. And that is definitely true. And in this problem, that would be 213 minus 44. But what is n? So what we know here is that n is going to infinity. So what happens as our denominator gets large, we can see that the value of that fraction goes to 0. So as we do an infinite number of rectangles, they become very, very thin. Question 6, how can you think of f of x and dx in a Riemann sum? What we were just speaking of here. F of x represents the height of each rectangle. You've seen this several times already. I hope this is becoming easy to remember. And our delta x becomes our dx, and that represents the base of each of those very thin rectangles. So an integral is accumulating an infinite number of rectangular areas. Is every function integrable? Is it always possible to find an area? Yes, if continuous, then it's very easy to divide the region into rectangles. And a jump discontinuity wouldn't even cause trouble if there's a finite number of them. So some jump discontinuities. So for example, if I had a step function, could I still find the area here by adding up these two rectangles? So a finite number of jump discontinuities is okay. You could still divide it into separate integrals or rectangles. Even a removable discontinuity, a hole in the graph, you could still put rectangles surrounding that hole in the graph, but an infinite discontinuity would be a deal breaker. No integral for us. Infinite discontinuity can cause trouble. All right, so let's take a look at a theorem here. So in future semesters of calculus, you'll study those special cases a bit more. But for now, we can say that if we know the function is continuous or has a finite number of jump discontinuities, then we could integrate simply by dividing it into Riemann rectangles. All right, let's try to tie FTC into what we've done before. Recall in a previous lesson, we did a Riemann sum with 1,500 rectangles, and we found that the area from 0 to pi over 2 under our cosine wave, so under our cosine graph, we found out this area was approximately equal to 1, and now we can verify that it is exactly equal to 1. So let's think about integrating here. What is the antiderivative? Cosine is the derivative of sine, so our capital letter F function is our sine wave, and then we're doing our evaluation theorem, capital F of B minus capital F of A, and there we have it. So indeed we know that the area under the cosine curve from 0 to pi over 2 will be equal to 1. All right, a couple more questions here for some understanding. I'm not quite sure how exactly you would get your car to change speeds this quickly, but if we were able to go 60 miles an hour, so this is a velocity curve. So if we were going 60 miles per hour between hours 0 and 3, and then somehow miraculously we were able to shift our car to go negative 60 miles per hour for the next 2 hours. I think, and I'm using this as a pretty simplistic example, but I think you know what you're doing here is that you would be moving to the right 180 miles, and then you're turning around. When your velocity is negative, you're moving to the left. So for 2 hours here, you would be headed back towards home 120 miles. So the displacement, again, just to make sure everyone understands that these are very different concepts. So your displacement would be 60 miles. Your total distance, however, and I'm going to give myself just a little bit more room because I want to put an integral there. Our total distance, you still have to put gas in the car so that you could travel 300 miles. So a very big difference between displacement and total distance. And what have we seen a minute ago here? That if you find the area under your velocity curve, that would give you displacement. So if we integrated from 0 to 5 of our velocity curve, that would give us our displacement. And our total distance, we would need to make it all of our velocity positive. So we would do that by using absolute value. And that would take that negative region and flip it up to be positive. So our total distance, we need to integrate the absolute value of velocity. And question 10, and then we'll take a break here. In question 10, consider the integral from 0 to 2 of 4x cubed. So we've got a cubic function that's growing pretty quickly here. Y equals 4x cubed. We know what that graph looks like. From 0 to 2, that would all be positive area. But then if we do our second integral from negative 1 to 2, what's the difference? We're adding some of this region here that would be negative. So we'd have negative area shaded in blue here. So we would think that that first integral from 0 to 2 of 4x cubed, that red area, is going to be greater than the integral when we put it together from negative 1 all the way over to 2. So we would expect our fundamental theorem would work out here. And I chose this function because it has an easy antiderivative of x to the 4th. So from 0 to 2 here, we would get 16 minus 0. And our antiderivative here of x to the 4th from, and these vertical bars here or square brackets mean the same thing, by the way. Here we're going from negative 1 to 2, so here we would have 16 minus negative 1 to the 4th would be 1. So our red integral would give us a region of 15, and when we start at negative 1, we've reduced, oops, I wrote that backwards. The red one is the 16. And when we start at negative 1, it's actually smaller. So the wider the interval does not mean we get a higher value. It depends whether the area is above or below the axis. All right, I'm going to pause here, and then in another video we'll work on homework problems.